All right, hey there. Here's the notes for 7-2, and here's the plan. Don't worry about printing these because I'm going to be working them on notebook paper also. But what I want you to do is just follow along with the notes and have a piece of notebook paper. I'm not expecting you to print these pages. Okay, so a couple formulas that I want to make sure that you know as we're going through this is our formula for exponential growth or decay. This is going to be a formula that we use to model real world population growth, radioactive material, and financial interests. When we start doing continuous growth or decay, we're going to talk about money, and then here's this E value again, and we'll talk about that in a little bit. And then you can know what each of these variables represents. So I posted 2 videos for you to watch about the letter E. This one's pretty short. That first one's pretty short, and it kind of talks about and shows you all about E. And I think it's an interesting conversation, especially when it comes to money. So if you have not watched those videos, go ahead and pause this one and take a look at those 2 YouTube videos to go ahead and wrap your mind around what E represents. I love the story of E because it is an example of where mathematicians found really a beautiful number and all about also making money. So follow along with this concept. Let's say that I put $1 in the bank and that bank offered me 100% interest. By the way, this is a crazy amount. Usually when you do a savings account, you get anywhere from 2 to 4% interest. That's a big difference. But the 100% interest allows us to show this math pretty easily. Okay, so your principal is the amount of money that you put in. That's your amount of money that goes in. The interest is the money that you earn. And then that is what is added to give you your total. So if you put $1 in the bank and the bank says, hey, every year we're going to give you 100% interest, you make another $1, and then that's what gives you a total of $2. That's pretty simple math because 100% is the same as 1, right? 1 times 1 is 1. That's the money I've earned. That's how much money I have. I started, I earned, I now have. Are we good with that? Okay. So let's start talking money-wise with percentages. There were people out there that said, hey, I like that 100% interest thing, but do I have to wait till the end of the year? Is there any way you could split that 100% into 2 payments of 50%? So the bankers were like, let's take a look at this and see if that works. If I multiply 50% times my $1 to get my interest, I'm going to realize that, hey, that's going to give me 50 cents. So the next time that I go to calculate my interest, I'm not doing it on my dollar because now I have $1.50 in the bank. This is what I have. So when I go ahead and I multiply $1.50, and we're going to bring our calculator over here. When we bring our calculator over here, we realize that the $1.50 that I have times the 50% interest is going to give me 75 cents of interest. So when I add that on to my $1.50, I don't end up with $2. Now I have $2.25. So this time that interest was taken at 100% one time a year, I got $2. But when I split that 100% into 2 50%, I ended up with 25 cents more. So then people were scratching their head. They were like, okay, wait a minute. What if we figured out a way to do it 1, 2, 3, 4 times a year? What if instead of giving us money once a year or twice a year, you calculated that interest more often, 4 times a year? So I want 4 times the calculations. Instead of that calculation happening 2 times, or as the bank would probably prefer it, 1 time. Okay, so let's take a look at what this math looks like. My 25% of $1 is equal to 25 cents. That's a quarter. So now I have $1.25 in the bank. And when I do 1.25 times 0.25, I get, this time around, 31 cents. And I have to add that 31 cents to the $1.25 that I have already in the bank. So now I've got $1.56 in the bank. So the next time that I have to calculate that interest, I'm going to multiply it again times my 25%. Hey, look at this time I earned 39 cents of interest. So when I add that to the money that I already have, I now have $1.95. I've got one more interest payment, which is going to give me 48, I'm going to round that up, okay? 49 cents added to the money that I already have. And now check it out. I ended up with $2.43. So if they do that same calculation once, I get $2. If I ask the bank to calculate it 4 times, I've just made 43 more cents. And that is because I'm earning interest on the money that I've already calculated. Okay, so you know people are greedy, right? Everyone's like, wait, what is the maximum amount of money that I can earn? So if you paid attention to the math that I was doing, I was more or less doing this formula. And what this formula is, how many times do you want the calculation to happen? And that is what's happening. I took my interest payment, my rate, and I said, do I want it 1 time or 2 times, which is 50%? Do I want it 4 times, which is 25%? Let's say I want that to happen 10 times. So my $1 is going to be multiplied by 1/10. So I'm going to divide it by the 10 times. I'm going to repeat that story is going to happen 10 more times. And did you notice each time I calculated my interest, I added it, and this is where it became an addition problem? That's what this is for. I'm adding it to. So when I go ahead, and I want you to check out my calculator here, when I go ahead and I say, okay, we're going to have my $1 plus that 1/10. So we'll go ahead and say 1 divide by 10, and then we're going to do that 10 times. That means I'm going to do that calculation 10 times. Check it out. Now I'm going to have a total of 2.59 cents. So then people, like, again, are crazy greedy. So with your calculator, you can come up and copy this formula. So now what if I want to say, okay, go ahead, do 1 plus 1 divided by 100 to the 100th power. Oh, I forgot my exponent. 1 plus 1 divided by 100 to the 100th power. Look, now I'm at 27. What if I said, okay, 1 plus 1 divided by 1,000 to the 1,000 power? So what you end up seeing is I'm not making as much of a jump as I was originally. Originally, I went from 2 to 225 to 243, but my jump is getting smaller each time. If I wound up graphing this, I would see that my jump levels off, and there's an absolute limit to how much money I can end up earning on that $1. So you see I was at 2.5, then I was at 2.7, then 2.71. You're like, wait, I didn't get a lot of growth out of that last one. Let's try one more. Instead of 1,000, we'll do 10,000. And notice this time, I only went up an even smaller amount. So what this number here winds up being is the limit. That's as high as we can go with this example of $1. So when mathematicians figured this out, this is what they decided was the absolute limit, and they ended up naming it E. So E is this beautiful constant that when they tried to figure out how to maximize their money, they realized this is all that you're going to be able to get. And I want you to think about, they figured this out back in a time where there was no electricity, no running water, no flushing toilets, and certainly none of these calculators. All right, let's talk about interest. If you borrow money from the bank, you pay the bank money called interest. And this kind of interest is the bad kind of interest. We don't like that interest because we're paying the bank to be able to have money. If I deposit money in the bank and I'm saving, the bank pays you money called interest. And that's the good kind of interest. That's where we're making money. And we can ask the bank, will you calculate it once, twice, 4 times a year, 10 times a year, or continually? And if they do it continually, we maximize the money that we get out of it. Okay, let's talk about what all these words mean, okay? This P is going to stand for your principal. That's the amount of money that you put into the bank account, okay? Here's E. It's our beautiful growth factor that ends up being about 2.718. And what E represents is that growth factor that's a constant, which means it's not going to change, and it's a beautiful irrational number that mathematicians discovered. It was actually kind of cool. Okay, so your rate is going to be the amount of money that you're earning, and you're always going to turn the rate into a decimal. And then by dividing by 100. So, for example, if you have 2%, that's going to turn into 0.02. 50% becomes a number like 0.5. So you want to make sure that you're careful with especially that 0. And then, of course, our T is going to stand for time. And that is usually based in 1 year. And we talk about this in terms of years. So if it's less than a year, you need to use a fraction. The good news is this is going to be our final amount. How much money do you actually have? And that's the formula we're going to use as we're working through our next examples. Okay, grab some paper. We're going to be doing some writing. All right. Jaden's parents invested $500 when he was born in a college savings account. Oh, let's label our notes 7-2 practice. And this is algebra 2. And we can go ahead and put the date on this. This is for the week of 4/27. Just so we know what crazy times these are. Okay. Jaden's parents invested $500 when he was born in a college savings account. The account's compound interest rate. As soon as you see compound interest rate, that means you know that it is the money that they're earning is compounding regularly, and that we can use the formula PERT. And that's the amount. So I say PERT because the amount that he gets is equal to the principal, the amount of money they put in, times E, times rate times time. So that E is going to be that constant growth factor. That's that constant growth factor. And that's just so cool that we figured that out so that we don't have to go through all those calculations over and over again. We can see that that's what's going to happen at with that factor of 2.7-ish. Okay, so the amount that he's going to get is equal to the principal. That's the $500 that they put in. And then we're going to use E. And they earned a 1% kickback on that. So my rate is going to be 0.01. And I'm going to do that for 18 years. So that's a quick calculator problem that we're going to be using when we go ahead and we put that into our calculator. So we'll go ahead and we'll say I have $500 and I want to multiply that by E. Remember, E is the second function above the division sign. And then that E is going to be to the parentheses 0.01% times 18. So the way that I typed this in is I'm going to make sure that this whole entire thing is in the exponent. So that means that by the end of those 18 years, Jaden's amount will be equal to $598.61. I think they better find a better account that makes more money. That's just what I feel. Okay, let's take a look at now problem number 2. All right, so problem number 2 tells us that Sharon takes out a loan to buy a new car that costs that much money. The interest rate is that much money compounded continuously. There again is that hint of what formula we have to use. If she pays the loan off in 6 years, how much has she paid total? Okay, so her principal times ERT is going to be equal to her amount. So the amount that she pays is going to be equal to that $25,000 that she borrowed times E, and that is going to be 4.7%, which is 0.047, and that is going to be times that 6 years. And remember, when you enter that into the calculator, this whole value has to be up in the exponent. Okay, so we'll go ahead and see what we have calculator-wise. So her amount is going to be equal to her $25,000, and that's going to be multiplied by E times E, and that's going to be to the parenthesis 0.047 is my interest rate times my 6 years. So by the time she pays off her car, her $25,000 car actually ended up costing her $33,000.47. That's crazy money, don't you think? All right, let's take a look at our next problem. All right, let's take a look at number 3. And we've moved out of our compounding continuously problems. So we're moving into just using exponential equations. And we do a lot of this conversation with population growth and decay models. The population of 1,700 elephants in a particular area is decreasing at a rate of 9% per year and can be modeled by this function. So here is the population over time is going to be equal to, this is my initial amount, that's how many elephants I currently have, and this is my rate of decay. And I know it's a rate of decay because remember it's that base value is greater than 0 but still less than 1. And then T is going to be those number of years that we've talked about since 2000. So if I want to find the population of the elephants in 2009, so what I'm going to know is that my population as a result of that time is going to be equal to this many elephants that I start with, but are decreasing by this amount for 9 years, because it's the number of years since 2000. So when I go ahead and I put that into my calculator, I can recognize that 1,700 elephants that are decreasing at that rate for 9 years is going to only leave me with 727 elephants. So that population change over those 9 years, I only have 727 elephants. Now, I can't really talk about a fraction of an elephant. You know that doesn't really exist. But we can still look at it as a model of how many around elephants. Okay. So now we want to take a look, and this is going to add to an extra conversation when we look at the second part of the problem, and it's going to say, during what year will the population fall below 500? So here's what's interesting, because what I want is, I don't know what this year is going to be, but what I want is to know at what point does this equation give me an output that is smaller than 500. So what point does this equation give me a value that is less than my 500 elephants? So now I'm looking at an interesting scenario because my unknown value is up in my exponent position, and I don't know how to solve that. So what we're going to do is we're going to go and we're going to look at and use the calculator as a resource. So I want to point out this part of the conversation into you. So what we're going to do is we're going to go to y is equal to, clear out whatever's there. We're going to plug in the left side of the equation into y1. So that's going to be y is equal to 500. The next side of our equation, we're going to plug the right side into y2. So we'll have our 1,700 elephants that we start with. We're going to have our rate of decay, and that's going to be to the x years, because we don't know how many years it's going to take for it to get there. Now, when I press graph, I'm looking for an intersection of a system, and guess what? I can't do anything because I can't see where that graph is. So I have to go and play with my windows. So if I go up to my window, I know right away I'm not going to have to deal with any negative x's, so I can just make that at -1. I know that I'm talking about a whole lot of years, maybe. I don't know. We'll see if we can see how many years until it gets below. We'll just make it 20. Our y minimum, our graph is not going to go below 0, but our maximum, I know I start off with 1,700 elephants. So I'm going to go ahead up to 2,000. Let's go ahead and see. There's my line at 500. And there I can see my elephant graph that is slowly decreasing. So now that I was able to change my window, I can go ahead and use second calc to find the intersection of where those curve. There's Mr. Blinky, he's on my first curve, and he says, hey, is this your first curve? You hit enter to say yes. He jumped up to my second curve, and he says, is this your second curve? Yes. He wants to know if you want to guess. You say no, thank you. And then he goes ahead and he gives you an XY ordered pair of 12.9. We're going to go ahead and round that up to 9/8. And then he's going to say 500 is where he found that intersection. So here's what I want you to think about what this is. We were solving for this, which is my number of years. And then this is going to be my number of elephants. So guess what? There's a very good chance that in 13 years, as we move past that, we're going to lose all of our elephants. So we'll say the 13th year after 2000. So I hope that way back in 2013, we didn't lose our entire elephant population, or that by now they're not all gone. That would be devastating. Okay, let's try our next problem. All right, bacteria can multiply at an alarming rate because each bacteria cell splits into 2 new cells, thus doubling. The function of, there's my equation, models the growth of 5 bacteria cells that double every hour, where X is the number of hours, during which hour will there be over 5,000 bacteria cells. So let's take a look at our equation. My number of cells is equal to the 5 bacteria cells that multiply at that rate, where X is the number of hours, during which hour will there be over 5,000 bacteria cells. That is another situation where I have my output, but I'm looking for and solving for X. So this is definitely tricky. So I'm going to go ahead and I'm going to go to my graphing calculator and I'm going to enter my 2 equations. Remember, we're going to look at the left side and the right side, and that's what's going to help us know. I'm looking for 5,000 bacteria cells, and my equation is 5 times 2 to the X power. So again, I'm going to have to go and adjust my windows. When I go to look at my first window, talking about my X's and Y's, I'm going to stick with my X is not going to go negative, and the maximum my X is going to go, we'll have to see how 20 works and probably need to adjust it. It's not going, my Y is not going to go below 0, but I'm looking for an output, obviously, that's pretty high, right? So what I want to do is we'll go ahead and put 5,000 in first. Maybe we should even go a little higher to 6,000. Let's go ahead and take a look, because there's my graph at 6,000, and there I am growing. So here is what I want to know, that intersection point. Second calc. I'm looking for intersect. My first curve, yep. My second curve, yep. Not going to guess. So my calculator is going to tell me that an input value of 9.9, and we'll go ahead and round that up to 9.97, is going to give me an output value of 5,000. So when I look at what that means, for my bacteria, that means after 9.9 year or hours, during that 9th hour, is when my bacteria increases to that point. All right, good job, everybody. So what we're going to do, we have one more. What we're going to do is talk about this last problem, and then we'll go ahead and review what I need you to do for your exit tickets. We'll go ahead and make this one number 5 real fast. Ready? The half-life of uranium, let's go ahead and make sure this is on my, there we go. The half-life of uranium is 6.89 years, which means it takes 68.9 years for the radioactive material to decrease by 1/2. So our function, our equation looks like this. The amount after some time is equal to 100, and this is e to the negative 0.01 t. That models the amount that's left from a 100-gram sample t years after 2000. How much of the original sample is present in 2257? First of all, we need to figure out how many years we're talking about. That looks like 250 years to me. So my amount after 250 years is going to be equal to 100 times e to the negative 0.01 times my 250, which is what goes into my calculator. All right, let's go ahead and do that calculation. We're back at the home screen, and we can say 100 times, and there's our e, the second division symbol, and that's going to be to the, make sure you have your parentheses, negative 0.01 times 250. So the amount of uranium that's left after 250 years is going to be equal to 8.21 grams. Okay. So make sure you do your practice homework. There will be a video for that and a Google form for you to turn in your answers for the exit ticket and e-card. So I hope you guys are doing okay and staying safe. Take care.